Hello everyone, my name is Hanjun Lee and I'm from Seoul National University. In this talk, I'm going to present NeuroSync, a scalable and accurate brain simulation system using safe and efficient speculation. This work was done with my fellow students and my advisor, Professor Jang-Woo Kim. Let me start with a brief introduction of the spiking neural network. Spiking neural network, namely SNN, models the mechanisms of the brain. It is essentially a directed graph whose nodes are neurons and the edges are synapses. To model the dynamics, each component keeps time-varying states. A neuron keeps two internal states called voltage and trace, and a synapse keeps weight. As the states evolve, a neuron may fire a spike. The spike triggers learning and changes the weight of the synapses according to the traces of the connected neurons. And the spike is transferred to the destination neuron. Note that the learning is also triggered when the destination neuron fires a spike. To simulate the dynamics, existing simulators adopt a time-precise method. The simulator divides the simulation time into short, discrete time quantum called time step. It sequentially updates the states for each time step. To do so, the simulator keeps a local memory of the states and a specialized data path to update the states. To simulate large-scale SNNs, existing simulators adopt a multi-core system to exploit the parallelism. In the multi-core simulator, the neurons and synapses are split into different cores, and each core simulates the dedicated set of neurons and synapses. The learning requires the traces of both source and the destination neurons. Therefore, the course also keeps and updates the corresponding traces. In addition, the multi-core simulator needs to synchronize the cores to ensure accurate simulations. Thus, the cores should handshake with each other and perform global synchronization at the end of each time step. However, there are problems of the time-precise method. First, a source neuron is connected to multiple destination cores and the corresponding traces exist across multiple cores. Therefore, it requires large per-core memory capacity. To make the matter worse, the trace update suffers from the low data reuse opportunity. In the time-precise simulation method, the traces are sequentially updated in each time step. Therefore, the trace update suffers from poor temporal locality, making the time-precise simulation energy inefficient. Second, the time-precise simulator suffers from high underutilization due to the frequent synchronizations among the cores. For each time step, the core updates the neurons and synapses. As the cores synchronously simulate the time steps, some cores suffer from idle cycles due to the load imbalance. Also, the global synchronization introduces extra idle cycles, waiting for the handshake among the cores. To mitigate the overhead, I'll briefly introduce our key ideas. First, we propose to collectively update the traces on demand. So, unlike the time-precise baseline, we skip trace updates in the absence of a spike. Instead, we update the traces when a spike triggers learning. By doing so, we update the same trace over multiple time steps and temporarily reuse the traces. Second, we propose safe speculation which relaxes the synchronization overhead of the time-precise baseline. In safe speculation, the cores synchronize only periodically and speculatively advance the time step within the period. Therefore, the cores suffer less from the idle cycles compared to the time-precise baseline. Note that safe speculation requires a rollback and recovery procedure to ensure accurate simulations. However, the rollback and recovery may critically affect the overall performance, so let's dive into the details. In safe speculation, each core speculatively advances the time step and updates the synapses upon firing spikes. When a core receives a belated spike, which should have arrived at T2, the core should roll back and recover the related neurons and synapses. During the recovery, the firing time of a neuron may change. In this case, the core suffers from a chain of rollback and recovery to cancel the synapse update using the spike at T5. And as a result, it suffers from high overhead. To solve the problem, we propose deferred learning. Deferred learning does not update the fan-end synapses when a neuron fires a spike. And the same situation, deferred learning does not suffer from additional rollback and recovery, as the fan-end synapses are yet to be updated using the misspeculated spike at T5. Therefore, it effectively mitigates the overhead. Note that deferred learning does not affect the simulation accuracy by selectively flushing the deferred learning, so please refer to our paper for more details. Now, we combine the three optimization schemes to design NeuroSync, which effectively tackles the problems of the time-precise simulation. Also, the evaluation result shows that NeuroSync achieves 3.81 times higher energy efficiency and 3.37 times higher speedup over the time-precise baseline. Thank you for your attention, and I'm more than happy to answer your questions. Thank you.